Hello, Applied 30. In our last lesson, we looked at optimization problems for the first time. We didn't really get to the end of it though. We kind of saw what they look like, we never solved anything. This time, I'm going to give you an optimization problem that we're going to work through, and it does have a full solution to the end of it. So the problem goes like this. There's a toy company that makes model sports cars and model SUVs. They can produce a maximum of 40 sports cars and 60 SUVs on a daily basis. The cost for producing one of those cars is $8, and it's going to cost them $12 to produce an SUV. The company must produce a minimum of 70 vehicles per day in order to keep up with demand. What we want to know is what the minimum and maximum manufacturing costs could be for this sort of company. And so this is where the applied math is really going to start kicking off. What information can we get from the problem, and how can we apply our knowledge of inequalities to figure out the minimum and maximum cost for this company? So a good starting point is to highlight any important information that we have, and then we can draw some conclusions from that. So the pieces that I've highlighted are there's a maximum of 40 sports cars and 60 SUVs. I've also noted that cars are going to cost $8 and SUVs will cost $12. And lastly, I've noted that the minimum amount of vehicles the company must produce is 70. Okay, so taking the information that I've highlighted, I'm able to draw some conclusions. First thing is that both my cars and my SUVs must be elements of whole numbers. I can't have a negative car or a negative SUV. I can't have a fraction or a decimal of either. That doesn't work. I could have 0, or I could have a whole number greater than 0 of cars or SUVs. So I've stated that first for both of them. Good habit, you should state that as well. The next thing is I'm not using it yet, but I'm just stating what the cost is. I know cars will be $8 and SUVs are going to be 12. And the third thing I've done is an inequality for each of them. So I know that X must be less than or equal to 40. I'm letting X be my cars. So I can have less than or equal to 40 cars. I can't have more than 40 cars, that's what my limitation was. And for my SUVs, I must have less than or equal to 60 of them. So Y is less than or equal to 60. I can also make an inequality with both X and Y because I know I must have greater than 70 because I need a minimum of 70 vehicles per day. So X plus Y is greater than or equal to 70. Okay, the one thing that was missing is I never spoke of my cost. That's because that's a part of my objective function. That's at the bottom. If we say C, that's going to be our new variable. If C is going to be our cost, C equals 8 times X plus 12 times Y. So once we figure out what X and Y could be in our optimization problem, we can figure out what the lowest cost, C minimum, or C maximum, the maximum cost, would actually be. In order to figure out what those values are, though, maybe we should graph our inequalities and find out if there's any points of interest on our graph.